SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 17 of the course E207 Electronic Devices and Circuits. So today I will talk about BJT as an amplifier part 2. In last lecture we discussed how BJT can be used as an amplifier. So we'll continue from here. My name is Deepak Jain. So if I talk about the contents, so in the last lecture we discussed several DC biasing configuration. So the role of DC biasing configuration is basically to fix the operating point. If you see these characteristics, IC versus VCC, let's say this is VCE. So these are the ICs for different IBs, IB1, IB2, IB3. So the DC bias basically fix the point, right, operating point, by fixing the IC1 and your VCE1 or whatever name you want to give. So we want this point to remain stable even if the temperature is changing and beta is changing. So that's why we try different DC biases, right? And on the top of DC bias we have the AC signal which will get amplified. So in previous lecture we talked about the fixed bias and emitter bias configuration. Right, we discussed two configuration, fixed bias and emitter bias configuration, where we found emitter bias is more stable. So today we are going to discuss about voltage divider bias configuration, collector feedback configuration, emitter follower configuration and common base configuration. These four configurations we will discuss, and then we will also talk about some different multiple BJT networks. So far we are using just one transistor. So in multiple BJT networks we can use several of them. So we are going to talk about that as well. And in next lecture we will discuss about the amplification, where we will use these configurations and we will use the input signal. Okay, so let's see. So first I will draw a circuit diagram for a voltage divider bias configuration. So as the name indicates, voltage divider bias. So voltage division is happening here somewhere. So just let me draw the diagram for this. So this is my NPN transistor and this is my current, let's say RE. This is one resistance R1, this is my R2 and which is again grounded, and this is connected to the some circuit resistance RC, and this is connected to the VCC. If you want, this can be your output through a capacitor, and this could be, there could be some input through resistance of the source, and this is your AC source. Okay, so this is where you apply the input. This is basically your input source. So this is input source, and if I draw an equivalent DC structure for this, that would be simply a resistance R1, R2. This is RE, emitter resistance, which is grounded. This is also grounded. And let's say this is common VCC, and this is RC, and this is connected to the. So here if you see and compare with the fixed bias case, the addition here is this resistance. This is new. In fixed bias case, what we had, if I just draw the DC equivalent for the fixed bias, so it was just like RC, RE, there was one base resistance RB, and both were connected to the VCC. Okay, so that's the difference between the fixed bias and the voltage divider bias. Why the name voltage divider bias is there? Because this voltage is being divided between these two resistance. So now we will see what's the impact of this additional resistance. The whole objective here is basically to make these biases more stable with respect to variation in beta. So what this additional resistor does. So that is interesting to see. So again we will solve the base emitter loop and then the collector emitter loop, and then we will see what is happening here. But before we do that, we would like to simplify this circuit. We will apply the Thevenin's theorem, which is well known and you must have done in the courses. You must have studied in electric circuit courses. So let me again draw the. So let me just again draw this circuit R1, R2, this is grounded, this goes to the, this is R and this is RE. Now, if I just consider basically this base emitter loop, right. So, this one, I can draw that part something like this. Okay. Using Thevenin theorem, where I will get RTH equivalent and ETH. So first what I need to do, I need to short circuit the battery. So what I get is R2, R1, and this is, let's say, short circuited battery. So in this case, RTH would be R1 parallel R2. So R1 and R2, this RTH will becomes R1 into R2 divided by R1 plus R2. And how about ETH? Okay. So ETH will become voltage drop across R2. So you can write, if we draw an equivalent circuit, that would be something like this. This is R2. So voltage drop across V2. So ETH would be R2 V2 divided by R1 R2. So using this Thevenin theorem, I can draw the circuit, this loop basically. So which will look like something like this, that I have a battery ETH or whatever name you want to give it to. This is grounded and this has a resistance RTH. Okay. So RTH is this, ETH is this, and this is connected to the base, and here is the emitter RE. So IB is going there, IC is here, and IE is here. So using this, we can basically calculate our IB current. This is what we did in case of emitter bias, fixed bias and emitter bias case. So now using this simplified diagram, we will calculate the IB, which is straightforward to do so. Let's do that quickly. So let me redraw it again. So it comes out to be ETH, then it becomes grounded. It has a 1 RTH. This is RE. So this is VBE. So, if I write KVL here, Kirchhoff's voltage law, so it comes out to be minus ETH, and let us say this is my current IB. So, it comes out to be IB RTH plus VBE plus IE RE equal to 0. And we know that IE is a combination of IB plus IC, and IC is equal to beta IB, which makes IE is equal to IB plus beta IB, and which makes IE is equal to beta plus 1 IB, and we can substitute this equation here. So, let me just take ETH and minus VB other side. It comes out to be IB RTH, and IE can be replaced by this term, which makes it beta plus 1 IB RE. If I take IB common here, it comes out to be RTH plus beta 1 plus RE IB, and it becomes ETH minus VBE. So, IB comes out to be ETH minus VBE RTH plus beta plus 1 RE. So, this is fairly easy to calculate. So, what we did here, this was the circuit, voltage divider bias circuit, because voltage division is happening here. So, we use the Thevenin theorem, and we calculated this RTH and ETH, Thevenin resistance and the Thevenin voltage, which comes out to be like by short circuiting the voltage, and the equivalent resistance comes out to be R1 parallel R2, and similarly the Thevenin voltage is across R2, which is R2 V2 divided by R1 R2, and the equivalent of that is been drawn here. So, using this equivalent circuit, we have just applied the KVL here in the base emitter loop, and we have calculated simply the current IB, base current. Now, you would say like the whole objective of this voltage divider bias configuration is to increase the stability against the change in beta. So, how is it going to help? How this base current is this design is going to help? Can we predict it from this base current, right? And how it is better than the fixed bias one, where we also had a similar expression for IB. Okay, so but before we, I can draw both of them and we can have a comparison. So, what is basically just to judge like what's the difference. So, here I will do the voltage divider bias configuration, and here is the emitter biased configuration. Okay. So, we can ignore the fixed bias because that we already proved in the previous lecture that the emitter bias is doing a better job than the fixed bias. Okay. So, if we correctly remember, IB is equal to VCC minus VBE divided by RB plus beta plus 1 RE. So, this was the expression which we derived in the last lecture, and the circuit was this. So, this is RE, this is RB, and some VCC voltage. Okay, very simple straightforward circuit. This you can say plus VBE, this is IB, and this is IE. And what is happening here is we are having ETH in place of VCC, and IB is going on, RTH is there, this is RE, this is VBE, this is IE. Okay. So, IB here is equal to VCC minus VB, sorry, ETH minus VBE divided by RTH plus beta plus 1 RE. So, this is what we just derived, right. So, if you compare both of these, more or less they look same, right. But then one can ask, like, what is the objective of this voltage divider bias 1 compared to the emitter bias. So, for that we need to go back to the structure, the circuit diagram, and then we need to figure out what makes this voltage divider bias configuration better than the emitter bias configuration, more stable than that. But if you just compare these two expression, here beta plus 1 Re is same. So, here Rb is replaced by Rth and Vcc has been replaced by Eth. So, does not look a lot of difference, but let us do a comparison, like what is happening here. So, let us go back to the voltage divider bias configuration structure or circuit diagram. So, this is Re, this is E, this is base, this is Rc, this is R1, this is R2. Okay, so this is base current and this is emitter current, this is collector current. These two are connected with the Vcc, okay, and these two are connected to the base. So, now the voltage drop across this and voltage drop across this should be same, which makes sense because the voltage drop between this point and this point, these two both are grounded. Okay, now let us say there is a current I and this is IR2 and this current is IB. So, current IR1, let us say, let me just use a subscript IR1 is equal to current IR2 plus current IB. Okay. Now, if I just let me take this point to be A and these grounded points to be B. So, VAB has to be equal to the potential difference between these 2 points has to be equal to IR2 multiplied by R2, and this has to be equal to the potential drop here, which is VBE plus IERE. Okay. So, this equation should hold true always. So, and we know that IE is equal to beta 1 plus IB. So, if I just replace this equation here, what I get IR2 into R2 is equal to VBE plus beta plus 1 IBRE. Now, if we explore this equation carefully for this circuit, what we get, see, if beta 1 increases, obviously IC will increase and this term will increase, this term will increase, right. If beta is increasing, this term will increase. So, in that case, what will happen? This term has to increase as well because potential drop has to be same. So, this term will increase because R2 is fixed, right. So, only the way for this term to increase is to IR2 to increase, right, to maintain the same potential difference. IR2 will increase, but we know that IR1 is equal to IR2 plus IB. So, if IR2 is increasing, right, IB has to go down. If IB will go down, then irrespective, even if beta is increasing, overall this term will go down. So, this loop basically helps to keep the beta, the impact of beta in control. So, this is, that is why this voltage divider bias configuration is better than the emitter bias configuration. There is no such feedback mechanism in case of a emitter bias configuration. So, let me draw all these 3 diagrams together, the fixed bias, emitter bias, voltage divider bias, so far what we have discussed, just to see and have a comparison that what is going on. So, This is fixed bias one. This is what we discussed in the last lecture, fixed bias. So here the diagram is VCC, this is RC, this is simply grounded, and this is RB. This is going inside this one. And remember, I am just drawing the DC equivalents. Okay, I am not interested at this stage in the AC one. So this is VBE, this is IB, this is my IC, this is IB. So here the current IB is simply VCC minus VBE divided by RB. Okay. And the case of emitter bias configuration, and this is the case of voltage divider bias configuration. So in emitter bias configuration, we have this VCC, RB, this additional resistance basically. So this is IC, this is IB, this is IE. Here IB comes out to be VCC minus VBE divided by RB plus beta plus 1 RE, and IC is equal to approximately, let's say, VCC minus VBE divided by RB plus beta plus 1 RE. And if I just again do that for this one, R1, RE, and this is my R2, this comes out to be this way, VCC. So the expression here is IBVETH minus VBE, where ETH is equal to R2 into VCC divided by R1 plus R2 divided by RTH plus beta plus 1 RE. So IC here becomes like ETH minus VBE divided by RTH plus beta plus 1 RE. And here RTH is equal to R1 R2 divided by R1 plus R2. Okay. So if you compare these three configurations so far what we have discussed, this is fixed bias configuration, no resistance here in the emitter. The difference here is resistance here, and difference here if you compare emitter bias configuration to the voltage divider bias configuration of this additional resistance. So that makes a lot of difference. Here there is no mechanism, like if beta is increasing, IB will remain more or less same, your IC is increasing. Here because of this distribution, this point, this junction, here you have IR2 and IB. So because of this same potential drop occurs here, IB can be controlled significantly. This way it can control the IC while changing IB. And here we don't have any term in the denominator. This is what we discussed in the previous lecture. So if I just say IC here is beta VCC minus VBE divided by RB. So you can see IC will increase dramatically, right? There is no one to control beta here, change in beta here. On the contrary, here there is something in the denominator. If it is increasing in numerator, something is there in denominator. So that will control. So other than that, this has more control because of this arrangement, and this works better. So that's why this voltage divider bias configuration is better than the emitter bias configuration. So now we will move to the next configuration, which is collector feedback configuration, similar to this voltage bias configuration where we have this mechanism to distribute the current and control the IB. Similarly, in collector feedback configuration, we do have some sort of arrangement. We'll see that what is that. So it is collector feedback. So this is bit different from whatever we have discussed so far. Okay. So what is happening here? Let me draw the structure VCC, the diagram, circuit diagram, RC. This is, let's say, output, and this is my resistance RE. So there is some current coming from here through a resistor RF, and which is connected to the base. And if I just want to draw the input, this is capacitor here, and these are two connectors. This is, sorry, RE. Okay. So if I see here, so what is happening here? The IB, the base current is coming from here. So this junction, this point is important. So there are divisions, two divisions of the current here. So you can see the current coming from IC is IC dash. IC is going in the transistor here as a collector current, and IB is going there. So IC dash can be written as IB plus IC, combination of base and emitter current. So again we will solve this, the DC bias circuit of this, and we'll figure out what are the currents here. And another important thing is that, because see, this is constant, let's try to understand that how it is working and why it is same as of, more or less same, doing the same job as a voltage divider bias arrangement. So what is happening here? See, IC is equal to IB plus IC. So if IC will increase, IB will go down, and we know that IC is equal to beta IB. So even if beta is increasing, but which will lead to increase in IC, IC will increase, IC will, this equation will lead to decrease in IB, and IB will decrease. So overall IC will remain same. Like this feedback mechanism is there. That is why this is acting same here as well. So same thing was here. So this is, that's why we call it collector feedback configuration. So that's why this arrangement is better than this fixed bias and the emitter bias arrangements where there is no such feedback mechanism is involved. So let's calculate the IB here, and let's see what is the value of IB here, like the equations. So we'll take a DC equivalent of the same structure, same circuit diagram, and then we'll apply the KVL as we have been doing in the previous case, and then we'll calculate the value of IB. So simple. So let's say this is grounded, this is VCC, this is going through RC, this is RC, the collector resistance, and then there is a feedback. Let's say this is my RF, okay, and this is going here. This is emitter resistance, and this is the grounded. So now I would like to apply this KVL into this structure, okay, into this loop basically. So what I will get is minus VCC plus IC dash RC plus IB dash RF, plus VBE, this is the voltage drop across here, base to emitter, plus IE into RE equal to 0. So this is the equation I got by applying KVL, Kirchhoff's voltage law, in this particular loop. I have done nothing, just use the DC equivalent of this and have applied this KVL, very simple, as I did in the other configuration case. So now let's simplify it and try to get the expression. So I will just bring down this expression back. which is minus VCC plus IC dash RC plus IBRF plus VBE plus IERE equal to 0. See, since the base current is normally small, so we can say IC dash is equal to IC and IE can be written as beta IB. So the equation comes out to be minus VCC plus ICRC plus IBRF plus VBE, and then this becomes plus beta IBRE equal to 0. Taking the voltages on the other side, it comes out to be and again this can be replaced as beta RC IB plus IBRF plus beta IBRE. So we can take IB common here and it comes out to be RF plus other beta terms, beta RC plus beta RE multiplied. So overall IB becomes VCC minus VBB RF plus beta RC plus RE. So this is the case for your collector feedback configuration. Which is more or less similar to others. If you see what we derived for voltage divider 1 VBE minus RTH plus beta plus 1 RE. Let me just show you. This is what we got for, and more or less this was similar for the emitter bias. But the difference between emitter bias and this collector feedback or voltage divider bias configuration is of this arrangement, right? This arrangement, this equation. So which keeps them in control. That's the basic advantage here. That's why these are more useful, common collector feedback and the voltage divider bias. Okay, so another one is the emitter feedback configuration. Okay, emitter feedback configuration. This is also known as the common collector configuration. So as the name indicates, collector is common here. Okay, so far we are discussing the case of common emitter, where emitter was common. Here the collector is common. So it's fairly straightforward. So this is voltage VEE. This is RE. This is capacitor, this is input resistance, and let's say this is capacitor and this is output. Okay. So this is a emitter feedback configuration, also known as the common collector configuration, and this is IE coming out of here. This is IC and this is I. So here you can say it is more or less but similar to the emitter bias configuration, but since the collector is common here, that's why it is known as the common collector configuration or emitter feedback configuration. So we will do analysis for this. We'll draw the DC equivalent of this and we'll calculate and we'll see what sort of current we get for this case. But as you can see from this circuit diagram, more or less it looks similar to the emitter bias case, emitter bias configuration. case. Okay, let's have a let's try to simplify this circuit and try to obtain an expression for IB. And let me just draw the DC equivalent of this, which is again very simple. So this is basically short circuited, oh sorry, grounded, and this is RE, this is grounded, and this is another resistance RB, base resistance, and which is grounded. Okay, so we will apply the KVL here, Kirchhoff's law, Kirchhoff's voltage law, in this DC equivalent circuit. So, and then we will see what is happening. So this is known as the common emitter case. Okay, now let me write down the equation for this set. It comes out to be, let's say this is my IB and this is my IE. So very straightforward, nothing to worry about. Sorry, this is VE, so this is a minus sign. So interesting thing that you need to keep in mind that this is minus VE, not just the grounded. I made a mistake there. So if I apply KVL, what I get is IB into RB minus VBE minus IE plus VE equal to 0 for this. And what I will get if I just simplify it, and assuming again, if you want, you can write I is equal to beta 1 plus IB. So what I will get is VE minus VBE is equal to RB plus beta 1 RE IB. So IB here comes out to be VEE minus VBE divided by RB plus beta plus 1 RE. So this is the base current here, and if you see this expression carefully, which is exactly same as it was for a emitter bias configuration. Let me go there and show you. Exactly same, RB plus beta 1 RE. So as I said, this is fairly close to the case. So this was one of another configuration, but as I said, voltage divider bias or collector feedback configurations are more popular because of their feedback mechanism. Another configuration can be is common base. So far we were talking about common emitters. Emitters were common in the first 3 then we talked about this common collector. Sorry, this should be common collector case, because collector is common here. So common collector case, and similarly we can have the common base configuration as well. I hope you can do that yourself. So now what the take home message from here is that the DC bias is very important, right? DC bias is very important. It decides your operating point. By operating point I mean in this curve IC versus VCC. So it decides where you are located, here, here or here, which region you are in. And the stability of operating point is also very important for the smooth performance of the amplifier. So this stability will be decided by the configuration which you can use. So different type of configurations we have discussed. Voltage divider bias is good. Collector feedback is also good. Because they have feedback mechanism. So somehow the IC should not change. with change in the beta. We have to design the bias. So of course these are the just few examples. You can design n number of configurations, n number of circuits just to control the this change if there is a change in beta, so that you can keep these IC and VCE in control. Okay, so once you decide this circuit, you have that, then amplifier can be made out of that. So these are the important things before amplification. So now we will talk about the multiple BJT circuits, what can be done, and of course in next lecture we'll continue about the amplifier. So let's move to the multiple BJT network. So far we have been discussing only one case where we have used one BJT. So now let's discuss the case where we have the multiple BJTs. What can be done? Can we use them in series and all that? What will be the influence? So that we'll discuss. So multiple BJT networks. Okay, so let me just quickly draw again in the voltage divider configuration here. So this is my output, and this will be connected through a coupler, a capacitor, and this is again there would be a capacitor for the input. So this will be connected R1, R2, this is the load resistor RL. So what do you see here? This is transistor 2 Q2 and this is transistor Q1. So the output of transistor 1 has been connected to the transistor 2 through this load resistor here at this point to largely constitute the base current basically, right, through these coupling capacitors. So this is basically, you can say this way, you can try to amplify the gain if you are using such multiple stages. So capacitor here basically makes sure that the DC bias of this and this are independent, only connects the AC signal basically. Also these bypass capacitors are here, they make sure that the AC signal passes through from here, short circuit, and doesn't change the bias point basically. Similarly here. So if I draw an, I'm just considering the case of two capacitors here, I can have a case of multiple, like n number of such capacitors. So if I draw a DC equivalent of this, it would be straightforward. We can keep them open circuits. So it becomes like a voltage divider bias configuration case. This is RE, this is R1, this is R2, and this is RC. Another case would be VCC. This is RC, this is R1. So same as we did there. So this is input, this is something like that. Okay, so their independent resistance, their parameter of the transistor, whatever beta 1 and beta 2 is here, they will decide all these parameters, applied voltage, etc., their operating points. But if you connect them this way, the AC signal will pass, the amplified AC signal will pass from here to the here. So depending on the characteristics, a wide range of properties can be obtained, which may not be possible in a single stage. So they can be arranged in a way that you can multiply beta 2 be beta 1 into beta 2 rather than just adding beta 2 beta 1 plus beta 2. So this way gain can be amplified dramatically. So this shows that there is a possibility of using these multiple BJT networks for wide range of applications. So we will discuss some of these cases, couple of these cases basically, and then we will finish for today. So the first one is Darlington configuration. So named after its inventor, Dr. Sidney Darlington. So here what happens, two BJTs are being used of same type. By same type I mean NPN, NPN or PNP or PNP, right? So what is happening here, the output of one stage, one transistor directly feed into the input of the other. Okay, so let me just draw it quickly. So this is happening, the output of the one transistor is the base current here for this one. I will just straight draw the DC equivalent. Okay, so let's say for this transistor it is beta 1, this is for beta 2. So you can see here the emitter is connected to the base of this transistor for Q1, Q2. This is base here, this is emitter, these are collectors, and this is emitter 1, C1, C2. So beta 2, B2. Now the equivalent beta for this is approximated as beta 1 into beta 2. Okay, let me derive this how it is. So here we know that IE is equal to beta plus 1 IB. Okay, and IB here, let's say I'm talking about transistor 2, and IB for transistor 2 basically is IE of transistor 1. So you can say IB of transistor 2 is equal to IE of transistor 1, right? And IE of transistor 1 is equal to beta plus 1 into IB of transistor 1. So IB of transistor 2 is equal to beta plus 1 into IB transistor of 1. And I just need to replace this equation here. So what I get, IE of transistor 2 is equal to, let's say these betas are different, beta 1 and beta 2. So this comes out to be beta 2. So it becomes beta 1 plus 1, beta 2 plus 1, IB Q1, or it can be written as approximately beta 1, beta 2, IB Q1. If I just say this is my beta equivalent is equal to beta 1 into beta 2. So the advantage of this Darlington configuration, as it is evident, this is one of the case of multiple BJT network, that two transistors have been joined together or connected together in such a way that to multiply their gain. So very high gain can be obtained, right? Suppose if beta 1 is 50, another beta 2 is 50, then it will just simply get scared 2500. This is a huge beta. It also, the advantage is high gain, and packaging can be done effectively, right? Two transistors can be connected together, very good, nice packaging in IC. Also, if you have two independent of these transistors, you can connect them. Also, very high input impedance. One of the disadvantages is that here this VBE1 and this VBE2 will be add up, so you need larger VBE. So in order to get rid of this problem, people have proposed another pair which is known as the feedback pair, also a complementary Darlington pair. So feedback pair, also known as the complementary Darlington configuration. So it is a combination of basically PNP plus NPN configuration. This is different from this. Here both are same. So what I have shown here is NPN plus NPN case, and this is PNP plus NPN case, complementary. So hardly there is any difference. The only difference here is that in this case, basically this PNP case or NPN case, let's say the output of this is going here. So this base emitter, so these VBE1, VBE2 are added together. So this voltage is higher. This is the case of Darlington configuration. And in this case, there is no such addition because one is of complementary in nature. So this can be something like PNP transistor, Q1 basically. So it is going to the another transistor's base, which is being shortlisted here, VCC, or there can be some resistance RC here, and this is my input connected through some base resistance, and this, let's say I'm talking about DC equivalent circuit here only. So these are the complementary transistors in nature. So this is PNP, this is NPN, right? So voltage here is just VBE2, whatever it is, to drive the circuit. So that's the largely the difference, but they are very useful. And one of the example of these BJT multiple networks. And if it comes to solving these circuits, like you can similarly take the loops and solve it. So I will quickly do that for Darlington configuration. I will just figure out the current IB1 and how it looks close to the other configurations that we have so far discussed. So let me just draw the DC equivalent circuit of a Darlington pair. So it is VCC going, this is, let's say, IC2, this is connected to the another transistor. Our base current goes, sorry, emitter current goes to the base, and this is RE, this is grounded, this goes to the RB VCC, this is IB1, this is IB2, this is IE1, this is IC1, this is IE2, and this is beta 2, this is beta 1. So IB2 here is equal to IE1. This is what we have done very quickly already. beta 1 plus IB. Okay, and we found that IE2 is equal to beta 2 plus IB2. And if I just replace it here, what I get is IE2 is equal to, let's say this is beta 1, beta 2 plus 1, beta plus 1, IB, and this beta D or whatever we want to notate, use the notations, beta 1 into beta 2. Approximations has been used here. Okay, so now we will apply the KVL here in this loop. Okay, so minus VCC and the first current IB1 RB base resistance plus VBE1 plus VBE2 plus IE2 RE equal to 0. Okay, so this comes out to be VCC minus VB1 minus VBE2, and this is IB1 RB plus IE2 RE, and IE2 we know can be written as IB1 RB1 plus beta 1 beta 2 IB RE. So this is where we can write this to be a sum of two voltages. So VBD, VBE for Darlington pair. So it can, if we take out IB here, so it comes out to be RB plus beta 1 beta 2 RE VCC minus VBED. So if we just solve it more, so what we get is IB is equal to VCC minus VEBD divided by RB plus beta 1 plus beta 2 RE. So this is the expression for IB, which is same more or less for the case of emitter bias configuration and other configurations. Similar expressions we have got, base resistance and all that. So this you can simplify, you can come up with your own configuration, you can combine several of these BJTs in different fashions to improve the performance in one or another way. Okay, so basically that was the objective, to improve the performance of these multiple networks of the BJT, and Darlington pair is one of the example where we use. The only difference in Darlington pair and the complementary pair is that here we use the same type of this NPN or PNP, and complementary we use one NPN, another PNP. And high gain, what we can achieve out of these pair is that a very high gain, high input impedance. So if I just quickly summarize what we discussed today, we discussed different bias configurations. We started from the review of the fixed bias, emitter bias configuration that we discussed in the last lecture. Then we moved to voltage divider bias configuration. Then we talked about the collector feedback configuration. Then we talked about the common collector configuration. And we found that if there is a mechanism in the circuit where if IC is increasing, IB can be reduced, that helps to basically keep the configuration or keep the circuit stable at a particular Q point, which is very, very important for amplification perspective. Then we talked about this multiple BJT networks where multiple BJTs can be connected in different ways to achieve something which is not possible by a single one. The example was a Darlington pair where input impedance is high and current gain is very high. It can be multiplied like beta 1 into beta 2. So that's we discussed, and in next lecture we'll talk about the amplifiers. Thank you very much. See you soon. Bye.